Hi everybody, so today I'm going to be presenting our submission to ICML 2024 called the Locally Interdependent Multi-Agent MDP. This is a work by me and my advisor Guanan Chu at the Electrical and Computer Engineering Department at Carnegie Mellon University. Now to sort of motivate what I'm going to be talking about, I want to bring your attention to some practical multi-agent systems which are decentralized and have local time-varying dependencies. So some examples include robot navigation, autonomous driving, UAVs. These applications are decentralized because agents could have some sensor limitations or communication limitations, and they have local time-varying dependencies because we want agents to achieve some sort of objective while maintaining some sort of local behavior. So if we take autonomous driving as an example, we want agents to get from point A to point B while avoiding local collisions. And in the case of UAVs, we might want agents to maintain some sort of formation while achieving the objectives. Now, much of this literature is empirical because of some challenges that discourage theoretical investigation. The curse of dimensionality. So just by virtue of having multiple agents, things become very intractable very quickly with the number of agents. The scalable RL literature tries to get around it, but it assumes fixed or stochastic dependence networks. And in our case, we have time-varying dependencies, so the literature there doesn't apply. We also have partial observability. Even single-agent POMDPs are hard to solve. And in our case, we have multiple agents, which makes it a DEC POMDP, and it becomes very intractable to solve in general. There's been a line of literature to consider to look for tractable special cases of DEC POMDPs, but as far as we know, this literature hasn't been able to tractably solve problems like what we're proposing here. So this seems like quite a difficult problem, but nevertheless we ask, can we theoretically model and find near optimal policies for decentralized agents with dynamic local dependencies in a scalable manner? And surprisingly, it turns out that the answer is going to be yes, we can. So for our first contribution, we propose a sort of setting here. It's a special case of the general multi-agent MDP, where each agent is going to lie within a common metric space X. We're going to assume that each agent has independent transitions. So intuitively, this is like the actuator controls for one vehicle shouldn't influence the behavior of another vehicle. We're also assuming that there's a speed limit enforced by the metric space. So agents aren't allowed to move more than a unit distance in this metric space. We also have that the reward function decomposes into the sum of pairwise reward functions. So in the case here that J and K are equal, this is a single agent reward. But in the case that J and K are not equal, this is going to be a reward function that is 0 when agents are far apart, and it's an arbitrary function when they get within distance r of each other. So each agent has a single agent reward, as well as this pairwise reward function that kicks in when agents get close. On top of this, we're going to enforce partial observability by saying that agents within distance v of each other can communicate, and all the agents that can communicate can take a centralized action together. Here we're going to propose 3 different policies which adhere to this communication scheme. So the first one is called the amalgam policy, where all the agents that can communicate, the group of agents that can communicate, take the optimal action just for themselves. And that's the amalgam policy. The cutoff policy is if we assume a setting where once agents disconnect, they're not allowed to reconnect. The cutoff policy is roughly the solution to that problem. And we also have the first step finite horizon optimal policy, which is the first step in the set of discounted finite horizon optimal policies with horizon C, this value here. Now, this is our main contribution here. We've shown for these policies that we've proposed that the performance of the policies is exponentially close to the fully observable optimal policy for the MDP. And here, this exponential constant C here is proportional to V, the visibility radius. And so as the visibility radius increases, the quality of the policy improves exponential relative to the optimal policy. And we've also shown a lower bound that shows that our policies are, that those bounds are near optimal up to constant factors. Now, the reason why this is significant is that in a lot of cases, computing these policies can be quite tractable. And here we have a simulation of the exact amalgam policy for 8 agents, and computing the optimal policy for 8 agents is very intractable, at least on the machine that this was computed on. And we see that since the group sizes don't exceed 3, we're able to very tractably find the exact amalgam policy for these 8 agents. And here we have a simulation of a similar setting where agents are trying to navigate to the center green square, but they don't want to get within 20 spaces of each other, and they receive a penalty for backtracking. And we see that as the visibility increases, the amount of backtracking decreases and the quality of the policy improves exponentially fast. Now, to summarize, we've created a new approach for finding solutions to DEC-POM-DPs, and we're very excited about the future works for this paper. There were some challenges that were omitted from the presentation, namely penalty jittering, which if you're interested, please take a look at the paper. And we also have some more simulations in there if you're interested. And to sort of conclude, I want to leave you with a sort of picture where if we imagine a world where all of the cars in the world have become autonomous vehicles, essentially we can model that entire system as one large locally interdependent multi-agent MDP. And if we overcome some of the challenges we describe in our paper, like large group sizes as well as this penalty jittering, we might eventually get to a day where we can solve this entire system tractably. And that's just a very exciting picture to me. And yeah, thank you for listening.